Start recording. So I'm audible, screen visible.
Yes, sir.
Yeah, okay. So let me just have a quick review and then we will start. So we started with this group theory, unit 4, where we defined group as having non-empty set along with a binary operation, ensuring that 4 of these axioms are satisfied. The closure, identity, which is unique in the whole group, inverse, which is unique for each element of the group, and associativity. We found that this commutative property is not mentioned anywhere. So groups are classified into abelian groups and non-abelian groups. Abelian groups are those in which the commutative property is also satisfied along with those 4 of these. So for set of elements to be group, commutative property does not need to be satisfied. But in case if it satisfies, then we call that abelian groups. We of course we took quite a lot of examples. One of the particular example which I have listed here is a dihedral group D3 with the compositions. So each of this element which is mentioned here, that's an operation which we performed on an equilateral triangle. So E, which is identity element, R rotation by 120 degree, R square rotation by 240 degree, L1, L2, L3. And the binary operation of composition is that if I am applying R dot L1, that I am going to apply first L1 on this equilateral triangle, which was originally given, and then I will apply R on that. We then discussed that there can be finite versus infinite groups. And then of course for the infinite we have the discrete versus continuous groups. We came up with this, that for finite groups there exists something what we call the order of the group, which is nothing but the number of elements in the group. And then we also discussed about an order of an element of the group, where that the minimum integer, positive integer, which will result in the identity element. Then we discussed about the cyclic groups, those groups which are generated by a single element, and then the generator of the cyclic group. So I have mentioned here with this white line that generally the cyclic groups, since they are generated by a single element, so it's common practice to write it in a triangular bracket with this element, which is the generator of the group. Then we discussed about the cancellation law and the permutations, that if there exists any group element G belonging to the group, then the composition of this group element with the entire group will not result in a new group, but will be the rearrangement of the terms of the original group. After that we discussed about the Cayley multiplication table, playing like a Sudoku, in which each row and each column will have all the elements of a group, but they all appear exactly once. And then we discussed that the 2 elements and the 3 elements groups are cyclic groups, and cyclic groups by nature are abelian, so they are abelian as well. And in both of these cases, the number of elements 2 and 3, we had only one possibility of the group structure, which means whenever you encounter a finite group of 2 elements or 3 elements, there exists only one structure, and that is what we call the cyclic structure of the group. And towards the end, I gave this question that try to find out 4 elements group, one with a square is equal to E and another is a square equal to B. So first I just wanted to know for second one, a square equal to b, what were the elements which you found? What happened to b square, for example, in this case?
E.
So in this case, b square turned out to be e.
Yes, sir.
And what happened to c square or ab?
B, sir. No, C
So what?
square B.
Sorry.
A square and AB is C.
AB
turns out to be C.
C. And this means what? Is it also BA?
Yes, sir.
Please check.
Yes, sir.
Yeah, yes, sir. It is also B.
BA. So if I take AB square, which means I take C square, what happens to this guy? AB times AB, and BA can be now being AB is equal to BA. I can write down AA BB, which is equal to what? A square B square, and each of them is equal to identity, which means C square is also equal to E. So this C, which is equal to AB, turns out to be nothing but the C square is also turned out to be E. Yeah. So what kind of group structure do we have here? A square is equal to B. Okay, B square turned out to be E, and C square turned out to be E,
Sir?
is it?
No sir.
Sir, B it was coming.
सर बी बी
सर बी
क्योंकि सर मिस्टेक कर दी सर, यहाँ ए स्क्वायर ई नहीं है सर, ए स्क्वायर बी है अपना।
A
यहाँ
square
आपने
B नहीं है?
सर A square B है.
सर जो आपने एंड में टर्म लिखी है ना, ए ए बी बी
Right.
इज इक्वल टू ए स्क्वायर बी स्क्वायर,
Right. So
देन यू
A square is
रोट
what? A square is, okay, this is what
B.
I was looking for. A square turned out to be B, E times E, which means this guy is equal to B, and C square turned out to be B. This is what you are saying, right?
यस सर।
Yes,
Yeah,
sir.
okay. Oh, okay. This is what I was looking for, that C square turned out to be B. But this is now interesting. Why this is now interesting? So A square equal to B, B square equal to E, and C square equal to B. So why this is interesting? So if I think about, let's say now C square, yeah, and which is nothing but equal to B. So what can I say about other things in this? Can I make something other, again E? Can I find out the order of the elements? Can I find out something else in this structure?
Sir,
Can I,
C4 is E.
so C square is
Sir, C to the power 4 is E.
C to power 4 is E. Okay, good. What about B? B to the power 2 is E, right?
E.
And A to power 2 is B. So which means what? A to power 4 is also
E.
E.
E. So what kind of order of elements are there for each of the group, or each of the element A, B, and C?
Order 4.
सर फोर्थ ऑर्डर फॉर
So
सी एंड बी, सी एंड ए।
so for C and A, you have fourth order, and for B,
इट्स 2 फॉर बी।
it's
2.
two for B or 4. The order is clear from this, right? For B, it is 2. For A, it is 4. For C, it is 4. Can you now think of any group which you have done up to now, which has this property, in which one element is of order 2, two elements are of order 4? Any group which you have done?
सर 1 -1 आयोटा माइनस आयोटा।
Okay, 1 minus 1 iota minus iota. Huh? So, okay, you will find out that this second one, absolutely right, that this table, the Cayley multiplication table, 1 minus 1 I minus I, will turn out to be the table which you have found for this group. Now, this group is also interesting in other sense. So, for example, if I want to write down a cube, yeah, which is nothing but a dot, let's say a square, what can you say about this?
AB.
AB.
ए बी।
This is a cube is AB. Yeah. So these kind of structures which you are finding, what about the A4? You have already found it is E, right?
Yes sir।
Okay. Can you say what is AB in this group?
C.
C, which you guys said here. So what is A cube? A cube turns out to be C. What is A square? A square turned out to be B. What is A4? A4 turns out to be E. So what kind of group structure is this? Where I have
सर साइक्लिक।
A4 is equal to E, then A square, then A cube, where A is of course A square is nothing but B, and A cube is nothing but C. So one of the possible group structure for 4-element group is what we have come up with, which is cyclic. Now, what happens to the other group structure, which is our 1? A square is equal to E. What happens to that? There you may have found out something interesting, that it is not going to give you exact unique result, but you would have found something. So A square equal to E. What about B square?
E, sir.
E.
You found it to be E, or there is a possibility that I could have chosen B square equal to A?
Yes, sir. It can be A or E.
Yes, sir. B square equal to A.
Either A or E. So let me choose one and then I will discuss about the other one. So B square equal to E. Let's say once I choose B square equal to E, what happens to the remaining term? C.
Sir,
Sir,
then
C square is also E.
C square is also E, but what was C in that case in terms of A and B?
AB.
AB.
Okay.
AB.
So in this case, C square equal to AB as well as BA again. You must have found out this thing. Yes, no?
Yes, sir. Right.
Yes, sir.
Yes.
AB gives C and BA also gives C. Is it true or not?
Yes, it's true.
True,
It's
sir.
true. That means that
Yes,
the
sir.
C square in this case will turn out to be something. This is what we wrote last time. But now there is going to be something interesting, that A square, B square, both of them are
E.
E, which is E. So in this case, this is what somebody said, I guess C square is equal to E. Now, what is the order of element in this group? This is a 4-element group. What's
2,
the
sir.
order of element? 2. Right. So that means what? Can I now say that 1 minus 1, I minus 1, the group which you had earlier compared with this part 2, can this also be compared with this one? Is structure
No,
1?
sir.
No. And is this group a cyclic group?
No, sir.
It cannot be, because none of the element is there with the order same as the order of the group, and hence none of the group, in fact none of these elements can generate the entire group. So this is definitely not cyclic. A square equal to E, B square equal to E, C square equal to E. This won't be a cyclic group. C is actually a product AB. In fact, if you take choice B square equal to A, then correspondingly you will find that C square is equal to E directly. This is what you are going to find. And that means what? That rest of the things which you have done with C is equal to A, B is equal to BA, you would have done it with B, and you would have ultimately found out the same thing what you have found earlier in this case. So was there the option that B square is equal to A in this case?
Yes, sir.
Yes, sir.
But then what was the option for C?
It will be E.
E, sir.
So C square equal to E. So you see that B and C are two elements which can be of course interchanged, and then the role of this C and B will be B will be interchanged. Which means what? That you are not going to get new group out of it. It's a group which will be exactly same as this structure 1. A square equal to E, B square equal to E, C square equal to E. The only difference will be that in this case you have found C is equal to AB. In that case you will find out B is equal to A times C or is equal to C times A. Nothing else. I mean structure wise there is nothing which is different. But now tell me, what happens to A square equal to E? Have you encountered any group of this kind up to now in which there exists this E and A, and with this, did we encounter any group like this? Only two elements with
Sir,
E
1
and
minus
A.
1.
1 minus
minus
1. We had that. And what happens to this two element group? This is always by
Cyclic.
default
Always cyclic and abelian.
cyclic. So what is
Abelian also.
interesting about this group? So even though I'm not going into the detail, you will find that this group can be written as the product of two groups. So right now I'm not telling you what is direct product, etc. But this is the interesting aspect of this group, that this particular Z4 a group which I am calling it Z4 can be written as the product of two elements group. For example, A square E and B square E. And since C is constructed out of AB, so I am not going to write for anything new. So this kind of structure is one possible structure for four element group. Another possible structure is the structure which we have given here, which is nothing but a cyclic structure. Fine. The one which I have written on the bottom, where I can write, actually I am not telling you how we are writing it, but it is just about that we have found two elements, both of which gives cyclic two element group, and third element which can be just made out of those two elements can be written in terms of these two. In fact, this is the only other option which you will find in case we are here. So this is called Weir group, after a German name actually. But four element groups, there can be two possibility. One can be cyclic, another is of the nature A square equal to E, B square equal to E, and C square equal to E, with C is equal to AB. So two things which you have achieved here. What? One, you have found the first group which is not only cyclic, but there is another option which is available. That's one. And two, you have started using the notation. I am not writing the Cayley multiplication table here, but I am writing all the essential parts of the table here in terms of this A square equal to B square equal to E, C square equal to B, resulting in this C4 equal to E, and so on and so forth. So this notation, the shorthand notation for writing the group, at times you will find out in the books where you won't find out that the entire group multiplication table is there. It is just the shorthand notation out of which we'll have to make a group. So for example, in this one, A square equal to E, let's say, is given, B square equal to E, let's say, is given, and then C is equal to AB is equal to BA is given. Then you can write down this unique group exactly in the manner in which you have reconstructed. I do not need to give you anything else. Out of these 3 points, you will be able to reconstruct the entire group. Questions here? That is how we make groups of higher orders. Okay, so how many how many structures are possible for 5 element group? Can anybody just guess if somebody has tried to look into it? What about the 6 element group? 7, 8, 100. So what does one need to do now? One needs to start thinking about, see, the possibility which looks like to be the case is that there always exists something like a cyclic group. So in 2 element it was there, in 3 element it was there, in 4 element it is there. There is of course a possibility in 5 element you just start making something like A square, A cube, A4, 6 elements, so on and so forth. But are there other possibilities also? Just like in 4 element group, there is another possibility, and we broke it down into two kind of a group. Are there other possibilities? If so, how to figure out? So our next sections will deal with that. But let's first start with what we call as the subgroup, a simple concept. A subgroup is something which is basically non-empty subset H of the group G. Now, whenever I am writing group, please understand this, and also remember that whenever I am writing this AB, it means that I am writing this A star binary composition. AB doesn't make much sense unless there is a composition, right? Okay, non-empty subset H of G, that means that H is contained completely in G such that 1, so H is of course set of elements. So I can write H1, H2, so on and so forth, such that H is closed under binary operation star, which it is inheriting from the group G. What is meant by closed? That if H1 belongs to H group, if H2 belongs to group, under the same composition, this guy will belong to it. So that is 1. 2, E of G, that is the identity element of G, belongs to H as well. Since identity element of the group is a unique element, so if H non-empty subset has to be group, so I should write A, then it has to meet 3 properties. One, it is closed. Another, identity element of the group has to be in H. And third, can anybody guess?
Inverse.
Right. If H is in H, so does H inverse. So if these 3 properties are met, then this non-empty subset H is called the subgroup of G, of the group G. And it is a subgroup in all sense. That means the binary operation is inherited from the group. You cannot decide to have new binary operation and call it subgroup. The binary operation will be inherited out of that. So questions here. What about the associativity? Why didn't I check it? I checked 3 properties: closure, identity, inverse. What about the associativity?
Because it holds, H is contained in G, that is why.
Right, since H is contained completely in G, so and it is for G to ensure that all the elements of G ensure this associative property. So all the elements of H will have to do it. So that means that each of this Hi surely belongs to G. It is part of this G, right? So G is a G1, G2, G3, H1, H2, H3, so on and so forth. So many elements were there. Yeah. So we divide it into 2 parts actually, the subgroups. One we call as the standard or improper or trivial subgroup. Can somebody think about the trivial subgroups of this group?
Sir, G.
Sure, very good. Since I have put this equal to sign that H is completely contained in G, so there is a possibility that G itself is a subgroup of a group. Anything else?
And sir, identity.
Right. If I have this E, then this will also form a group. We remember that the single element group is there, E, the cute little one. Of course, a dull one, but it's there. But these are called, of course, the trivial ones. So what would be the proper subgroups? Proper subgroups are all those subgroups which are not G and E and which will meet the properties as mentioned above. Yeah. So for example, let's just think about it. 1 minus 1 I minus I. Can you think about any subgroup of this guy?
Sir, 1 minus 1.
1 minus 1.
Okay, let me just make H is equal to 1 minus 1. Will this take care of all the properties? H is closed, so 1 and minus 1 of course belong to the larger group. Under complex multiplication, I mean I will write it just to remind you that the group always has that, but closure there for both the elements.
Yes, sir.
Yes,
Identity,
sir.
Yes.
inverse of both.
Yes, sir.
Yes.
With
Yes, sir.
respect to if we consider multiplication.
Multiplication.
Addition, sorry.
Yeah, it is the same. You cannot change this operation. Sure, under I cannot talk about a subgroup
Yes,
where
sir.
the binary operation is changed, right? Right, sure. Under same binary operation, let me emphasize it. Yeah. And then what are the other subgroups? What about 1 and I?
No, sir.
Sir, closure is not
Sir,
satisfied.
iota cross iota will not give element from that group.
What about 1 I and minus I?
No, sir.
Why? So again,
Sir,
the
because
minus 1 is not there.
I
What
star
about
I
1
is
minus 1 and I?
No, sir.
Sir, inverse of beta is not there.
Yes,
No,
sir.
not there. Okay, so interestingly, it looks like that you have found out a subgroup which is a proper subgroup. Is there any other subgroup which is possible for this group?
No, sir.
No, there will be trivial subgroups which will be a group having only one, and of course so there are three subgroups for this one having exactly the same order as G, another having exactly order 1. And what about this guy? What is the order of this subgroup? H.
2.
What is the
1.
order of the group G?
4.
4.
4.
G has 4 and H has either 1. What is the order of group H? This was 2 or 4. So this one is for this guy, another is for this guy, another is for this guy. So interestingly, I do not have any subgroup of order 3 coming in here. I have only subgroup of 1 to 4. Okay, we'll just keep it in mind. So let me just come up with one homework here. And what will be that? Since I like this D3 composition, so group, what was the group D3? This was E, R square, L1, L2, L3. So your job is to find out all possible subgroups H. I mean, whatever number you are able to find out. Fine. And then divide it into proper and improper, figure out whatever you can. For example, if the subgroup is cyclic or not. In particular, I wanted to just write one because I have already used this property something. ERR square. Is this a subgroup?
Yes, sir.
So how did you manage to make it so fast? I mean, did you say it?
Because like the rotations were independent of the flipping which we considered. So
Rotations are independent of reflections, huh? But it is also clear from if you go to the table which I have asked you to make, which is the Kelly multiplication table for this, just look at this block which has E, R and R square. Does this block having E, R square on the column side and E, R square on the row side have all the elements which are required here? That means E, R square only. If so, then you can actually get an idea of the subgroup from the Kelly multiplication table as well. Or I said that I like to say group composition table. Yeah. So please see that. So this
Yes,
is
sir, it has.
yeah, this is question. This surely is a subgroup. Is it a proper or the trivial?
proper.
Sir,
Proper.
It's a proper one. It does not, it is not identity. It is not group itself. Yeah, good. By the way, there is another way of actually detecting a subgroup rather than checking all the individual properties. So if H is contained in G, then this is a subgroup if for each pair of elements Hi, Hj belonging to this subgroup H, we have Hi inverse, Hj also in H. So I'm not going into the proof. And those of you who are still not clear how we are writing, this is the binary composition, which is of course there. So somehow it can be shown, not somehow, it is easy to show actually, that if two elements are in H, implies that Hi inverse times Hj is also in H, then this is a single property which tells you that H is a subgroup of the bigger group G. So, okay, without proof, I am giving you this another way of figuring out. Okay. Questions here about the subgroups? Okay, larger question still haven't answered. If I go for, remember the question which we were discussing? if we are going to figure out, let's say a group having elements 100, 200, 900, whatever it is, then what are the possible structures or what are the possible orders of the subgroups which are possible? Is it that all possibilities are there, or there are certain possibilities which will be eliminated? So for that to happen, for that to answer, we will have to first come up with the concept of cosets. Now, cosets, you can just read it as co-set, which means that I am talking about set and some co of this set. So coset, that's the name it is. And it will be clear as soon as I will start discussing about it. So what is this concept of coset? Let H be a subgroup of G. So that means that H is going to have elements, let's say H1, which we may define as E, okay, H2, H3, so on and so forth. Yeah, and let X be any element of group G. Now this X, of course, there is a possibility that this X is contained in this H, or this X is not contained in H, but is contained in this G. There are two possibilities, right? But what is important here is that if we make X times H, which is basically writing X times H. So what are we writing basically? We are writing X composition H1, X composition H2, X composition H3, so on and so forth. So we are multiplying this group or composing this group by this X from the left hand side, so that we are going to get the elements X star H1, X star H2, X star H3, so on and so forth. If E is H1, then this first one will become X itself, right? Then we call this guy the left coset. I'm just giving you the definition right now, and we will dissect the definition later. The left coset of a subgroup H is nothing but the product of H with all possible X's which belongs to G. So can you give me the tough one, the right coset then? Definition only, nothing beyond that.
Sir, Hx equals
Hx, right? Which is identical as H star X, which H1 star X, H2 star H, H3 star X, so on and so forth. So the definition wise, it is rather simple, that the cosets can be left or right depending upon the composition of this subgroup with this element X, whether it is coming from the left side, whether it is coming from the right side. If it were an abelian group, of course, you would not have worried about it. I will come to that again, but the definition wise, it is just that simple. Now, let's just try to understand what will happen if X belongs to H and what will happen if X does not belong to H. Let's just see. So let's say if X belongs to H, then what will happen if I do XH? So you have H, H1, H2, and one of the element is X, and so on.
it should give H only, I think.
So think about it. If I take composition of this element which is already there with any of the element which are already there, and H is, remember, a subgroup, very important to remember. So then this will be what?
Sir, we'll just get permutation of the elements.
This you will get the permutation of the elements H, and this is what we utilized in our Cayley multiplication table already. So this is of course not an interesting thing. It is something which is the second one. Let's say X does not belong to H, but X belongs to G. What will this give? So this is rearrangement, and in case it is identity, right? Nothing beyond the identity, then it is the group itself again. What if X does not belong to H? Can you tell me now? This is something interesting. Whether you're going to If I construct XH now, can this guy have any element common with H? So this is the question which we are trying to answer now. Of course, I can actually prove this, but I can also take an example. So let me just take an example and just try to do that. We have already done what? 1 minus 1 I minus I as a group of 4 elements. Let's say this is my G, and let's say H under multiplication, complex multiplication, and you have already given me 1 minus 1 as a subgroup also under same, of course. Yeah. Can we build all possible cosets for this H? So let's just build first one, I cross H. Can you build this coset for me?
Sir, iota minus iota.
So this will be iota minus iota. Okay. Can you also build this guy then? Which is identical as writing IH minus IH. Left coset. Yeah.
1 minus 1.
Minus
Minus
iota and
iota
1.
and
Iota.
Iota. Okay. Now, can you tell me something? Whether IH, which is, let's say, the first left coset which you have made, does it have any element which is common with H?
No.
No, sir.
So
No, sir.
this guy does not have any element in common with H. Okay. What about minus IH?
No,
Does that have any element which is common?
No.
No. So does this give you an idea what is going to happen? To my question?
sir, it does not belong to H then. XH also.
So what you seem to be getting is this. You actually are getting plenty of points, and I am going to discuss that. First, that number of elements in this left coset, any of the left coset which we have made, is exactly the same as the number of elements in H. In fact, there is this order of H which is also defined. What is this? In this case, 2. Yeah, order of G is 4. So, number of elements in left coset is same as order of H. So that is one. That is one thing you have found. 2. None of the element in XH is same as H. That is what I have written, XH in section H equal to 5. It is very easy to prove it also, and we will prove it. But then there is a third one also. Can you tell me any of the coset which you have made? Is it a group or not? I minus I or minus I. H
No, sir.
surely was a subgroup. What about IH?
No.
Why it is not a subgroup?
Sir, closure is not satisfied.
Anything else?
Sir,
Identity.
Identity is missing, right? I mean, you do not even need to go for closure. There is no identity. Identity was already there in H. And now that you are making this group, you considered only those elements I minus I which belong to G, but none of it belong to H. Because if you consider those elements which belong to H, then you would have got, of course, only H, right? So then there is no point of going for the left coset, etc. So what does that mean? That cosets don't form a subgroup if, of course, X does not belong to this. Yeah. And the second one is also true for the same thing. Cosets don't form a subgroup. And that is why you have to think about a nomenclature of these guys. And that's the reason why we have come up with this nomenclature. It is called cosets, that these guys are sets and they are core to this subgroup. Existence of these sets without thinking of a subgroup doesn't make any sense. It's like a dangling pointer in our C. I mean, you cannot have a pointer which does not point to anything. Otherwise, it is a very dangerous thing. Similarly here, so the name Coset, now you can actually decipher it. The set word is that these guys are sets and they are co to H. You change H, the cosets will correspondingly, you will make new ones. Yeah. So the word coset is coming because we are talking about sets which are co to this subgroup H. That is how this nomenclature. And let me just now prove our point 1 or point 2. None of the element in XH is same as in H. So let me just try to prove that. So we start with if X does not belong to H and X still belongs to our group. Let's say sum, our proposition, sum X times HI belongs to H. एक एलिमेंट है जी जो x times hi which belongs to H, and this is for sum hi. Yeah. Now, can you tell me what about hi inverse, where this guy is? If hi is in H, then where does this hi inverse live in?
H only.
Sir, in H only.
In H only, sir.
In H only. So now, can you tell me if I operate hi times hi inverse, where does this guy live in? This is in H as per our proposition, and this hi inverse is also in H.
In H all.
So this belongs to H. This belongs to H. This is what we are saying as the propose, that there exists one. So this belongs to H. Now we know our, what is this property?
Associativity.
So associativity has to be there because it's a subgroup. So hi inverse, what happens to X? Hi inverse. What is this guy?
Sir, identity.
And what is X times identity?
X.
X belongs to H. But look at this. This is what we started with. So this gives me a contradiction. We are saying that only possibility for XHI, any element, for is even if a single element, to be in H is that if X belongs to H. If X does not belong to H, then you cannot have any element of XH common with H. That means that the intersection of the two has to be a null set. Questions on this part? It's a very important thing to remember.
So please explain it again, sir.
Yeah, okay. See, we are saying that what do we want to prove? We wanted to prove point 2. None of the element in XH is same as H. So for example, so 1 and -1 was there. So none of the element of any coset which you build can be 1 or -1. This is what we want to prove. So what we start with, we are starting by proposing exactly opposite. So this is what we want to prove, that if X does not belong to H and X does not, and X is still out of G, then there exists. So we are just saying, proposing that let's say there exists some element such that X times HI belongs to H. And remember, this XHI surely belongs to your XH. This is the coset definition, right? That when you have H, which is given as H1, H2, so on and so forth. And if you create XH, then you have XH1, XH2, so on and so forth. So you are saying, let's say there exists one element, XHI, which belongs to both. So this is how you are starting. Let's say there exists one element. So if this belongs to both, then what happened? Then I say that we already know that HI inverse should surely belong to H because that's the subgroup H. And hence, product of the two elements, that is, product of any two elements of H should still remain within H. That is by definition of the subgroup, that it has to be a closure one. Since XHI belongs to H, HI inverse belongs to H, so the product of the two should belong to H. But then I see if that happens, then by using the properties of the associativity and the identity, it automatically means that X has to be in H itself. But that's what we were not talking about. We are talking about all those elements which does not belong to H. What are these guys? They are going to give cosets, and none of the element of this coset is same as any of the element of H. This is the interesting part we are saying, that H and XH cannot have any element in common. You got the point?
Yes,
no?
sir. Got it.
Yeah.
Quite
Good. Good. So let's just continue to, and not only that, we also said the number of elements in XH is same as the order of this H. It cannot be any different also. It is exactly same. So now let's just go and do something more with this, what we are doing. Fine. So let's say we have XH and H. We already know that H intersection XH is phi, and we also know number of elements of XH is equal to order of H. Okay. Now let's say one more element. Now this guy belongs to group. This guy does not belong to any of this guy. What does that mean? Because if it belongs to any of these guys, then you won't get something new. But there are two possibilities in this case, that you can think about Y does not belong to XH, or second, you just say that Y does not belong to H, but Y still belongs to XH. Yeah. So two things. Third, in case if you want to, that Y belongs to H. So tell me first, in this case, Y, okay, Y belongs to H, which I am writing as the third one, Y belonging to H, can Y also belong to XH?
No, sir.
Why not?
So the intersection is phi.
So H intersection XH is phi. So the only possibility for this one is? Yeah, so you have only these possibilities and there is no other possibility, right? So let's just look at the third possibility first. Y belonging to H, but Y does not belong to XH. If I make a coset YH, yeah, what will be this? So think about it again. In this one, H1, H2, so on, and there exists one element Y. And surely that this element Y, so X H1, X H2, this Y of course cannot be there in this guy XH. That we have already proved. So what happens to this Y times H? If I try to make a coset YH, what does that mean? I'm talking about?
So it will be same to H.
Sir, H itself.
This is the same as the subgroup, so it is not going to give me something new. So it's a case which does not matter much to us. Let's just consider these cases, the upper one. Now let's say this one. What happens if Y belongs to H, but so Y does not belong to H, sorry, but Y belongs to XH, and I try to make YH. What can you say about this guy? Is it same as XH? It is different as XH, or it may have certain elements which are different. Can you say something about it? So if you are unable to think about this,
It should be same as
let's
XH,
just
I
think
think.
about it this way. My examples are best way to think. So you built IH, right? You built IH and you got this I minus I, which is your coset. Yeah, I minus I. If you take any element out of this, let's say minus I, and you now say that if I am going to make another coset out of it, what will be that? So minus I belongs to IH, but minus I does not belong to H. What kind of result it will be? Is it a new coset which you are going to get? Is it the same coset which you are going to get?
So same coset.
The same.
Yeah, so interestingly, this can be shown that in this case, you will find out that there exists only one possibility, that YH is equal to XH. The third case is very interesting, where I am saying Y does not belong to H and Y does not belong to XH. It does not belong to any one of these two. Yeah. What will you say about this YH, which now I will try to make? Will it have any element which can be common with H? Will it have any element which can be common with XH? How many elements are there in this YH? Can you say something about it?
No elements.
Sir,
No
will it
elements in
even
common?
exist?
Say it again.
Sir, will it exist?
Why not exist? I mean, think about it. I have given you 4 element group, but oh god, there can be 2 element group, right? 6 element group, out of which so many of those will be there. Yeah, I mean that group will, like, I mean, surely it will
Sir,
exist.
sir, G minus union of XH and H.
Yeah, I mean, so think about this way. If you do not want to think in this one, so think about it in this one. So L1, L2, L3, there exist these, yeah, and you will find out interestingly that EL1 form a subgroup. Yeah, so this will be L1 square is equal to E, and this subgroup will be cyclic, abelian, whatever you know of this. This will be a subgroup, you will figure out. And then let me take first one, L2H, let's say. Since it does not belong to H, I can just think about making this. Yeah, so you will make L2 dot E, and then you will make L2 dot L1. But will it exhaust all the possibilities? You can have L3H, right? You can have RH, you can have R square H. Yeah, there can be so many elements which can be there in this group. Why to limit yourself with 4 only, right? Even in 4 there exists this minus I, which does not, I mean in this case does not seem to be making any of the difference. But if you just enlarge the group, there will be plenty and plenty of elements, right? Yes, no?
Yes, sir.
Yeah, please.
Yes,
Please understand that this can exist easily. I mean, there will be so many cases in which it will be. And I am talking only about the 6th one. There may be even bigger ones. But let's say, so I will discuss about that soon. And unfortunately, I'll need to close this topic also. So I will take 5 minutes more. So let's just try to think about this case 1, where my Y does not belong to XH and Y does not belong to H. What will happen in that case? I will just do the proof exactly in the manner in which I did the proof earlier. Yeah. So let's say for some YH, we have, let's say this belongs to XH. So we are saying that in general, Y belongs to group, but Y does not belong to XH and H. However, there exists something like this where YHJ belongs to XH. Then that means what? That means YHJ should be one of the element of our original XH. Yeah, right? The one which I have written
Yes.
as the second one.
Yes, sir.
This has to be there.
Yes, sir.
Yeah. So now, what about if I multiply with HK inverse from both the sides, or HJ inverse from both the sides? Will HJ inverse and HK inverse belong to what? This belongs to
H.
both of these belongs to H, right? So let's just do that and tell me what happens. So YHJ, HJ inverse. Where does this guy belong? XHK, HJ inverse. Where does this guy belongs? So
H.
where does HK, HJ inverse belong? That is simple.
H.
H. Where does X times any element of H will? X times any element of H?
Sir, XH.
XH, right? Now let's look into the left hand side. What has this left hand side now? This
Y.
is only this guy. This guy becomes y is equal to x hk hj inverse, right? I mean, I am not putting this associativity and the identity, but this is rather simple to see that you are getting it. So y is equal to this. That means the only way a possibility exists is y also belongs to xh. So if that to happen, then okay, our original idea that y does not belong to xh, that's not true. So it is again by contradiction we will show, or we have shown that none of the element of y times h can be in xh. I mean, that of course cannot be in h, we already know that, but it cannot be in xh as well. So that means that we have come up with something new. If y does not belong to xh and h, then y intersection xh, what can you say about this? Okay, y. So let me just write down first and then you figure. Okay, so I have written this three things. So yh intersection xh, what is that?
Sir, phi.
Phi, if of course y does not. If y is one of the element of xh, then what is happening? Our case 2.
Sir, same as XH.
So same as xh, there is no new. It is again a rearrangement, right? What about h intersection xh? That we have already proved. Okay,
Sir,
I
phi.
do not need.
Phi.
What about yh intersection h? It cannot be anything. So what am I going to? What am I going to get is rather interesting concept, which is what I am going to write. So let's say there exists a bigger group and let's say there exists some subgroup. H is always subgroup, G is a group. Now, if I have element X which does not belong to this H, then you will have set of elements XH which will have no element in common with H and which will have exactly the same number of elements as the H is. Yeah. And if there are some other elements Y which is not there in H and XH but which belongs to G, then it will result in another one. And that way, that means that you can partition your whole group. So group is partitioned into disjoint cosets of subgroup H. So this is where I will end my today's lecture, that what we have learned out of cosets of H, that this cosets of H partition my original group into disjoint union. And this will result in something which will be very interesting in group theory, which is what we are going to do next, but not today. Does somebody know what is this theorem, Lagrange theorem?
Yes, sir.
What is that?
Sir, order is finite. Order of subgroup is finite, I guess. Muljeet.
It is not only about the finite. Finite groups is what we are considering right now, right? So what will be the order of the subgroups? That is what we are going to go about. But okay, questions on today's point. What we try to prove is simply a very simple one. I mean, simple thing, which we try to do is this way, that we come up with the concept of subgroup, but we still could not partition the entire group out of this subgroup. So what we have done, we came up with this concept of coset, which is of a subgroup H. And these cosets are very interesting in some sense that these cosets do not have any element which is common with H if this element which you have chosen is not in H. If you choose, if let's say H union XH, if this gives group, then it is surely true, that there does not exist any Y in that case, which will be out of H or XH. But if it is not true, then you can continue to do this. union YH, and that may give group. If that is exhausting the group, it is fine. If it is not, then you can continue to build this. So you have union of these groups. Each of these H with XH, H with YH, H with ZH, they are all giving the disjoint ones. So they are all giving the intersection, which is 5. This is what we have to. Okay, questions? No. So what I am going to do about the book, I am going to upload certain number of pages. I mean, the one which you have read, which book you read? I mean, just remind me. I did mention this contemporary abstract algebra, I guess, Gallian, right? Those who have read it, those who haven't read it, okay. So you can continue to, of course, look at that because that's an exhaustive book. But what I am going to do, I am just going to upload a set of pages from some book, of course, and you just go through the group theory which I am doing up to the point of group theory. Once I will reach to representation theory, I will change my text and reason other things. But in order not to populate your mind with too much text, or not too much text or too many pages of the text, I will just upload few pages, and those pages, please go through those. Try to understand if you are able to understand the properties. In case if you are not able to understand the properties, of course, you will fall back on some other book, and then I will tell you other references. But group theory is such that again, it consumes lots and lots of pages of the text. So I will upload something and will let you check that. And questions, if at all, on today's class? Okay, I am hearing continuous point, but no noise. Okay, let's just finish it off then. Thank you, guys.
Thank you, sir.
Yeah.
Thank you, sir.
Hello, sir.